Okay, and we should be up and running. Let me just check the audio. Is the audio good? Actually, my screen's not being shown. Just give me a second. Let me just add it back. There you go. And the camera. Okay, cool. Nice. So I've decided, and my audio is I'm getting some feedback. Okay, good. I've decided to actually go for um, references and pointers instead of constant expressions, just because I feel I can come back to this later, and I want to really crack on and move on. So we'll do reference pointers, then we'll do enums, and then we're getting into classes, which is the interesting thing and the main reason why I'm doing C++. Um, and then functions, operators and overloading, inheritance, which is related to class, and then you're getting into classes. Okay. Anyway, so we're gonna, if you would like to do constant expression functions, feel free to do it. But I think if I need to, I'll come back. I can always come back to it. So I'm going to move on actually to compound type references and pointers. So I'm going to create a new chapter. So I'll do chapter 16, compound types, and then we'll scroll all the way down, and then 16 compound. Cool, nice. Yeah. So I don't actually know too much about pointers and references. The only thing I know is that the pointer is with the asterisks, and the reference is with the ampersand. That's about as much as I know. But anyway, let's get on with it then. So you can see it's quite a big chapter, and so are enums and structs and classes. But this is really the main thing with C++, from what I've heard. Okay, so intro to compound data types. So, what's that? So the fundamental data types are things like booleans, strings, integers, chars, things like that. So if you wanted to multiply two fractions, you might do it like this. Numerator 1, denominator 1, numerator 2, denominator 2. Use the use to eat slash remove slash. Okay, so the basically the ignore white space. Okay, and then we do that. While this program works, it is quite a lot of dry. Do not repeat yourself. Exactly. Well, if you had 100 employees, you wouldn't want to do it forever and ever. So, C++ supports a data type called compound composite type. These are types that are defined in terms of other existing data types. Compound data types have additional properties. So it's like if you were at the gym and you were doing a compound movement, like a deadlift or something, and you're essentially hitting more than one. Compound is more than one muscle group. So that's basically what you can use that for. So additional properties and behaviors that make them useful for solving certain types of problems. Every data type is either fundamental or compound. Okay. So C++ supports the following compound types: functions, C-style arrays, pointer types, pointer members, reference types, enumerated types, and class types. So we've already done functions. I don't think we've done arrays in this, but I have used arrays before. Pointer types we haven't done. Pointer to member types, no. Reference types, no. Enumerated types. I've done enumeration in Swift, but I haven't done it in C++. And classes, like structs, unions, structs, classes, and unions. I've done structs and classes in C++. And in Swift, and classes in C++. In Swift as well. So functions, pointer types, pointer to member types, data member types, reference types, L value and R value references, enumerated types, unscoped and scoped, class types, and these being structs, classes, and unions. Okay, so that was that. Value categories, L values and R values. So I assume R is reference, but I don't know what L would be. Okay, so nice. So now we're on to the second part. Um, okay, so value categories, L values, and L values and R values. So, okay. So we know that an expression is a combination of literals, variables, and operators that can be executed. So for example, this would be an expression 2 plus 3, producing 5. We know that we have increment and decrement or decrement operators, and you can use prefix or postfix. For example, 5, and for example, 5, and then that will turn into 6. So all expressions in C++ have two properties: a type and a value. So a type of an expression, the type of the expression is equivalent to the type of the value, object or function that results from the evaluated expression. So the result. So basically the result. For example, we have our main function. We have auto v1 because we can use auto to allow the compiler to compile it for us, or not compile it, deduce it for us. So 12 divided by 4 will be an int divided by an int, and that will result in an int. .0 divided by 4, as we know from previously, is a double divided by an int, which will produce a double. And then as always, we need to return 0 for our main function. Yeah, hopefully that makes sense. It does to me. Right. Yes. Because if they don't have the same operands, it will fail to compile. compiler can use the type of expression to determine whether the expression is valid. So we have a void print with an integer parameter of x. Then we have a standard character output of x, and then we print foo, because this will produce an error because we're expecting an integer, not a string. Okay. A value of a value category of an expression the value category of an expression indicates whether an expression resolves to a value function or an object of some kind. So we got integer of x unassigned. X was now equal to 5, but we cannot make 5. 5 is a literal, and we cannot assign it to that. One of these assignments is valid, i.e. this, and one is not. The answer lies in the second problem, the value category. The value category of an expression indicates whether the expression resolves to a value function or object. So it's what value can be assigned to it. So L value and R values. Okay, I think I'll do another. Yeah. L value and R values expressions. An L value expression no, I was wrong. It's not reference, it's literally left and right. An L value expression left value is an expression that evaluates, i.e. equals to, or results in, evaluates to an identifiable object or function. Entities with identities. Entities with identities can be assessed via an identifier. So entities with identifiers can be accessed via an identifier, reference, or pointer, and typically have a longer lifetime than a single expression or statement. So, for example, X is the identifier, and now X is the L value. In the above program, the expression X is an L value expression as it evaluates the variable X, which has an identifier. So, for example, the expression of X, i.e. int X 5, is an L value. As it evaluates to variable X, which has an identifier. X is an L value Okay. X is an L value expression. Right. Since the introduction of constants into the language, L values come into two subtypes: modifiable, and non-modifiable. Such as const. Okay. L values have two sub types: modifiable a value that can be modified, non-modifiable a value that cannot be modified, e.g. const or const expression. So for example, we have an integer return type for our main function. We have int of x, so this is unassigned but it's modifiable. Const double d, so this is non-modifiable. Then we have int y of x. X is a modifiable L value expression. And then const double e. D is a non-modifiable L value expression. And then obviously we need to return 0. That makes sense. So an R value now is the right value. Is an expression that is not an L value. R value is expression of evaluates to a value. So actually I need to get rid of that, where I mentioned here oh no, that was fine. An R value, right value, an R value expression evaluates to a value. Commonly seen R values include literals, a return type, a return value for function, and operators that return a value. R values aren't identifiable, meaning they have to be used immediately and only exist within the scope and expression of the expression of which it's used. So let's do it ourselves. So I'm going to include for the preprocessor our input output stream. We're going to have an int return 5. Then we're going to simply return 5. Then in our integer return type main function, we're going to set x equal to 5. So 5 is an R value. So it's basically the right hand side of your expression is a R value expression. because usually you would have, in other languages, you have equals. So this is the left-hand side, and this is the right-hand side. But since we're doing list direct list initialization, we don't include the equals. Const double d of 1.2. So 1.2 is an R value expression. Then we have int y of x. X is a modifiable L value. Const double E D. D is a non-modifiable L value expression. Then we have int z, and we're going to be returning 5. So return 5 is an R value expression, since the result is returned by value. So return 5 is an R value expression, since the result is returned by value, i.e. this. Then we have int w of x plus 1. So x is a modifier value. X is an R value expression. So x plus 1 is an R value expression. Because it evaluates, or it has a value, whereas L value identifies to an object. And that's why our return 5 creates a value, but also because it's literally on the left-hand side. The right-hand side. So that makes sense that x plus 1 is an R value expression. Then we have int q, and we're using static cast typing. So this would be a right-hand side. Yeah. Q, and we're using static cast to convert it. Static cast, the type will be integer. So we're converting d, the double, to a integer. And then returning 0, as always. So the result of static casting d into an int is an R value expression. Okay. That's sort of beginning to make sense. I mean, surely it's just if it's on the right. No, it's. I was about to say it's only because it's on the right hand side, but x is an L value, and um, that is because it evaluates to an identifiable object. X is the object, whereas this evaluates to. This is an object, but then you're modifying the object by creating more value to it. So, the best way to think about it is L values, left value expressions evaluate / equal to an identifiable object, whereas an R value expressions evaluate to a value. Okay. Value categories and operators. So it's not just as simple as being on the left-hand side or the right-hand side. Value categories and operators. So we know that with operands, the left-hand side and the right-hand side must be the same, otherwise you'll get an error. Unless specified otherwise, operators expect the operands to be R values. For example, binary operator plus expects operands to be R values. So, for example, and again, I know it's very basic, but the preprocessor include input-output stream header, a return type of integer for our main function. Then we have a standard character output of 1 plus 2 with a line break, and we're returning 0. So does that mean our main function is L value? I think so. So 1 and 2 are R values because they evaluate to a value. Now we can answer the question why x is equal to 5, but 5 is not equal, 5 to x is not valid. An assignment operation requires its left operand to be modifiable L value expression. The latter 5 equals x fails because the left operand 5 is an R value, which means it's not because it's not modifiable. So again, I know it's very basic, but I just want to drill it into my head. So a preprocessor of include We got an input output stream. We got a return type of integer for our main function. We're setting x to be unassigned. Assignment requires the left operand to be a modifiable L value expression and right operand to be a R expression. So this is valid as x is a modifiable L value expression, and 5 is a R value because it evaluates to a value, i.e. the integer of 5. Whereas this is not valid as 5 is an R value expression, i.e. It evaluates to a value and x is a modifiable L value expression. And then we have return 0. And as you can see here, the expression must be modifiable L value. So, okay, nice. So, L value to R value conversions. L value to R value conversion. Since assignment operations expect the right operand to be an R value, you might be wondering why the following works. So in cases where an R value is expected, but L value is provided, the L will undergo a conversion from left to right value so that it can be used in such contexts. This basically means the L value is evaluated to produce its value, which is an R value. Okay. The best way to think about this is an L value which evaluates to an object will implicitly convert to a R value, which evaluates to a value. This means that an L value can be used anywhere that an R value is expected. An R value which evaluates to a value and does not evaluate to an object, on the other hand, will not implicitly convert to an L value. But I assume that potentially you could use explicit conversion, but we'll see. So we have a x is our L value, so we're doing x so x is our R value. No, sorry, x is our L value. And then we're converting x to an L value because, well, sorry, we are converting our x being an L value to an R value because we're no longer pointing to an object, we're creating a value. Is that why? In this statement, x is being used in two different contexts. On the left-hand side, x is an L value, yes. On the right-hand side, x undergoes L to R conversion and is evaluated then so that 2 can be used for the plus. Yes, that does actually make sense. So how to differentiate between how to differentiate L and R values? You may still be confused about what type of expressions qualify for L's and R's. For example, the result of an operator plus an L value or an R. So the best way to think about this is an L value expression which points to an object are those that evaluate to an object, aka functions or identifiable objects, including variables that persist beyond the end of the expression. And remember, the expression is just the line when this occurs. An R value expression is one that evaluates to a value, such as x plus 1. This includes literals, and temporary objects that do not persist beyond the end of the expression. So, finally, we can write a program that tells the compiler, we can write a program and have the compiler tell us what an expression is. The following code demonstrates a method that determines whether an expression is an L or R value. So we have our headers, whether the preprocessor of include, of input, output stream, and string. T. So we then have a template type name T. We have a constant expression Boolean, is value, and then we have a reference, but we haven't got into that yet. Return true. So T and is an L value. This is because it points to an object. Yeah, it evaluates to an object, aka functions or variable. T and is an R value reference. Why is that the case? So this overload will prefer R values. So why is that an R value? Is it because of the reference and the ampersand? That is an R value, which makes sense. Hopefully that'll come a bit more clear, I guess, in the future. So this method relies on two overloaded functions. Yes, correct. One with an L value parameter and one with an R value. The L value reference version will be preferred for left and the R value. Thus we can determine. Okay. So that was L and R values. And we know that a. No, I don't want to save that. I want to save this. We know that an L value will implicitly convert to an R value. When needed, but an R value will not implicitly convert. Okay, that's the main takeaway. And an R value evaluates to a value such as, where's my x plus 1? X plus 1, but an L value evaluates to an function or an object such as a variable or a literal. Okay. L value reference, i.e. the ampersand, I believe. Yeah. Okay. So I'm just gonna take a quick break here, and then I'm going to do earn value reference, and then yeah, I'll be back in a minute, and we can do value references. Cool. Right, we still good on the mic? Let me just check. Yeah. Okay, so now we'll move on to L-type references. Remember that a L value, sorry, reference. An L value is something that evaluates to an object, like a function or a class or whatever. But a R value is something that evaluates to a value. Yeah. Okay. So, right. L value references. So, in C++, a reference is an alias for an existing object, which is what we did briefly with, I cannot remember what it was, but we did type references or alias for like we would create a namespace for a value. Sorry, for an identifier. Which would be the object. So once a reference has been defined, any operation on the reference is applied to the object being referenced. This means we can use a reference to read or modify the object being referenced. Okay. A reference is essentially identical to the object being referenced. A reference is essentially identical to the object being referenced. Okay. You may also create references to functions, though this is done less often. Modern C++ contains two types of references, an L value reference and R value references. So, L value reference types. Types. So an L value, which evaluates to an object, an L value reference type acts as an alias for an existing L value, such as a variable. Just like the type of an object determines what kind of value it can hold, the type of a reference determines what type of object it can reference. L value references can be determined by a single ampersand. So maybe that's why he knew that the function in the previous lesson was a right, because maybe an R value it uses 2, perhaps. I don't know, I'm guessing. But if I'm wrong, I'm wrong. You know, what are you going to do? So regular types. So we have int, a normal int type, not a reference, int and an L value reference to an int object, double and an L value reference to a double object, and then a const int reference. An L value reference to a const int object. For example, int ampersand is the type of L value reference to an int object. Yeah, that's basically what we just did here. The type specifies the reference. A type that specifies a reference. The type that can be referenced is called a reference type. I don't think I can say that any better, so I'm just going to copy that. Okay. So there are 2 kinds of L value references. There are 2 types, 2 kinds of L value. And remember, L value evaluates to an object, R value evaluates to a value. An L value reference to a non-const is called an L value reference. An L value which evaluates to an object reference to a const is called a we'll focus on non-const reference this lesson. Yeah. So L value reference variables. Okay. One of the things we can do with an L value reference is create an L value reference variable. Okay. An L value reference variable is a variable that acts as a reference to an L value. So I think I'm going to have to write this down. One of the things we can do with L value references is create an L value reference variable. This is a variable that acts as a reference to an L value, usually another variable. Okay, so to create an L value reference variable, we simply need to define a variable with an L value reference type. So I'm going to do this here. So we got preprocessor of include, and we got our input output stream header. Include spelled correctly. Then we have a return type of integer for our main function. Then we have an integer of x of 5. X is a normal L value int variable. Then we do int and ref x. Ref, i.e. this one, is an L value variable that can now be used as an alias for variable x. So essentially now x, we have x here, but we can use ref instead of x as well. So this means when we do standard character output x with a new line, and we also do standard character output ref, and you can see here we have int ref referencing to this, and then a line break, and then as always a return 0. So we run this in our terminal, and eventually you see we get 5 and 5. So print the value of x, 5. Print the value of x via ref. Cool, that makes sense. So when defining a reference, place the ampersand next to the type, not the reference variable name. So the best practice when defining a reference is to place the ampersand next to the type, not the reference variable name. Like this, basically, is what he's referring to. Modifying values through non-const L value reference. Okay. in the above example, we showed that we can use a reference to read the value of the object being referenced. We can also use a non-const reference to modify the value being referenced. So where am I? Let me just clear my terminal and create more space. So in the previous we now know can use a reference to read the value of the object being referenced. We can also use a non-const reference to modify the value of the object being referenced. Now remember that I just want to hammer it home again and again. When we're dealing with L values, that L values are ones that evaluate to an object, and R values are values that evaluate to a value. So let's practice that. So we got an include input output stream header. And then in our integer return main function, we have an integer of x being assigned to 5. We have an integer reference of x. Ref is now an alias for that. So then we produce x, print it rather. Then we then have x being equal to 6. So we've now converted it to 6. So x now has a value of 6. Then we have a standard character output of ref, which again refers to this. So this prints why does that print 55? Oh, because you have x and ref. My bad. So he's done that, and then we've done that, and then we'll do that. Yeah, that makes sense. This will print 55. This will print 66. Then we do ref being equal to 7. And then we'll do a standard character output x and ref, and then a line break. And we know that this should print 77. Ref now has a value of 7. But so does x. And then as always, we return 0 in our main function. So we run that code. As you can see, we get 55, 66, 77. So in the above example, ref is an alias for x. Yes, so we're able to change. Yeah, that makes sense to me. So reference instantiation. Oh, this is a big one. I don't know if we'll finish it by the end of this stream. So I'm just going to take a quick break here and then we can continue with reference initialization. Okay. Right, let's continue then. Okay. Okay, right. Where were we? We were on reference in initialization. Okay. Must likes constants or references must be initialized. Fairly straightforward. I don't think I need to type that out myself. So that's an invalid reference. Okay. When a reference is initialized with an object or function, we say it's bound to the object or function. So when a reference is initialized with an object or function, we say it is bound to said object or function. Then the process by which such a reference is bound is called reference binding. Non-const L values, which evaluate to objects or functions, can only be bound by modifiable value, L value. So a non-const L value reference can only be bound to a modifiable L value. So this is okay. Yeah. Such as, so we have our main return function, we have an integer of x, and we set that to 5. We then have int reference of ref referring to x. Then we have a const int of y to 5. And then we have an integer reference to invalid ref, which itself is referring to y. And then we have int and invalid ref2, which is initiated with 0, a non-const L value. Non-const L values can't bind to an R value because they have to reference. Okay. So that's invalid because it's a L value can't reference to a non-bindable, non-modifiable. This is invalid because i.e. the reference must refer to an already established L value and cannot create one. If non-const L values could be bound even though, okay. So, a reference will usually only bind to an object matching its reference type. Yeah. So a reference will usually only bind to an object matching its reference type. In most cases, a reference will only bind to an object whose type matches the reference type. If you try to bind a reference to an object that doesn't match its reference type, the compiler will complain and implicitly convert the object to a reference type and then bind it to that reference type. Yes, it does mean that because, yeah, that's what I thought. Since the result of a conversion is an R value, because we are creating a result, we are evaluating to a value. A non-const L value reference can't bind to an R value because you cannot make an R value equal to an R value. Trying to bind a non-const L value, which evaluates to a object that doesn't, trying to convert a non-const L value reference to an object that does not match its reference type will result in a compile error. So, and I think it's best to write this. So we have a return type integer main. We have a integer initialized as 5. Then we have our int reference ref where we refer to x. So that's okay because it matches. Then we have a double of d initialized as 6.0. Then we have an int reference of invalid ref, and we're going to be initializing it with d. So this is not valid because we're creating a return type of integer, but the return type should be double. Then we have a double ampersand, a double reference for invalid ref2, and we're creating that to be x, but we know that x is an integer. Invalid non-const L value reference can't bind to an R value. Yes. And as always, we return 0. Okay. References can't be reseated, changed to refer to another object. Once initialized, a reference in C cannot be reseated. A reference in C cannot be reseated, meaning it cannot be changed to reference another object. Okay, so it essentially becomes, your reference essentially becomes constant, right? Even if you're not using it to reference a constant return type. Sorry, reference type. Yeah. So consider the following program. So we have our preprocessor of include, and then we have our input-output stream header, and then we have our return type of integer main. So then we have int x being 5, we have int y being 6, then we have our integer L value reference of ref being referred to x. Ref is now an alias for x. But we try then to do ref equals y. This assigns 6, not the value of y, to x. The object being referenced by ref. The above line does not change ref into a reference for y. So then we do a standard character output of x, and then a line break, and then return 0. So this assigns 6. So because ref, I think it's best if I did it to explain it to myself. So we got the preprocessor of include input output stream. We got a return type for our main function. We got int x being 5, int y being 6, Then we have our reference to x. So now reference is bound to x. Then we want to change ref to 7. This means now that x becomes 7. This is because ref is, this is because the ref variable is an alias for x and is not replacing y. So essentially what you are doing is the same as if you did x equals 7. So when you print x, sorry, no, that should be y, my bad. X becomes 6. So when you print x, because the reference can change, reference refers to a modifiable value, it will change x. For example, standard character output x when a reference is evaluated in an expression, it resolves to the object it's referencing. So if ref equals y doesn't change ref to now reference y, rather ref is an alias for x. The expression evaluates exactly to x equals y. Yes, that makes 100% sense. As Patrick Starr says, that makes sense to me. Okay, reference scope and duration. So as we know from previously, usually local variables are created here and then they die at the end of the block. So, yeah, we should finish it by today. Okay. Okay. Reference variables follow the same scoping and duration rules as normal variables do. Yeah, that's fine. Reference and reference have independent lifetimes. with one exception that we'll cover in a later lesson. With one exception, the lifetime of a reference and the lifetime of a referent are independent. In other words, both the following are true. A reference can be destroyed before the object it is referencing. The object being referenced can be destroyed before the reference. I think that makes sense. I just need to probably see it in action, like with most things. So when a reference is destroyed before the referent is not impacted. So a reference is this one, but a referent is this one. When a reference is destroyed before, so this is the reference, and this is the referent. Let's again do it. So preprocessor include input output stream. We have a main return type for our main function. We have an int x5. So this is the referent. Then we have a nested block of int reference ref, and we're referring to this despite the fact that it being outside the nested block. Ref is the reference to x. Then we have a standard character output of ref, and then a line break. This prints 5. The reference of ref is destroyed here. Then outside the nested block, we do standard character output x. This still prints 5. And then we have return 0 and our x, the original reference. No, the original referent is destroyed here. And you can see here we should get 5 and 5. There you go, nice. When ref dies, variable x continues normally. Yeah, perfect. Dangling references. Dangling references. When an object is being referenced, when an object being referenced is destroyed before a reference to it, the reference is left referencing an object that no longer exists. This is known as a dangling reference. Accessing a dangling reference can lead to undefined behavior. Okay, so we're not doing that yet. So yeah, so we'll do this and then we'll call it a day. Just need to charge. Okay. References aren't objects. No, they're just aliases for objects. So references aren't objects. Perhaps surprisingly, references aren't objects. A reference is not required to exist or occupy storage. If possible, the compiler will optimize references by way of by yeah, cool. I just want to check something. By replacing all occurrences or references with the referent. However, this isn't always possible, and in such cases, references may require storage. This also means that the term reference variable is a bit of a misnomer, as variables are objects with names and references aren't objects. Yeah, I think the best way to think about this is perhaps that it's not an object. This is because you're just creating an alias for an object, and an alias is not an actual thing. Like Heisenberg is an alias for Walter White. Heisenberg is not. Sorry, Walter White is not Heisenberg, but Heisenberg is. Walter White is a person, but Heisenberg is not. Not a person. He's an idea, so he's not an actual person / object. And that's the way I'm at least going to think about it until I'm proven wrong. In cases where you need a reference as an object or reference that can be reseated, reference wrapper provides a solution. The best way to think about it is that you are creating an alias, and an alias is not a real thing. It's like a pseudonym. It's fake. It's a fugazi. It's fake. It doesn't exist. You know what a fugazi is? Anyway, so quiz time. Determine what values the program prints by yourself. Do not compile the program. Okay. So here we have, and I think it's probably best to do it here. So we have our preprocessor of include. I know he said don't compile, but I'm doing it in my notes, so it won't actually compile. Input output stream. We have our return type integer for our main function. We have int x being 1. We have int and ref referring to x. So this is the reference for rather 2x. X is the referent. So then we are printing x ref with a line break. So this will print 1, 1. Then we are creating a y variable of 2, and ref equals y. This means that we are essentially doing x equals y. So for as ref is an alias for x, so at this point x equals y, which means ref and x equals 2. Okay. Then we're setting y equal to 3, which is completely separate from x and ref. As ref cannot be reseated to y. So then we're printing standard character output of x and ref, and then a line break. So this will print 2. Then we're setting x equal to 4. Then we're printing x ref. Now, I'm in 2 minds, and then returning 0 as always. Now I'm in 2 minds of this. We're setting x equal to 4. So the R value of x is now 4. And I assume that ref will follow as well. So this will print but if ref does not follow, this will print 4.2. We had an example identical to this. Yes, so when you change x, it means you change. Okay, so I think then this will print so I think the above will print 11, 22, 44. Let's have a look. Nice, cool. So it was. So that was good. Good to know. Yeah, cool. So because ref is bound to x, x and ref are synonymous. Yeah. So they will always print the same value. The line ref y is essentially x equals y. It does not change or reseat ref to y. Okay. Nice. So I think we'll call it a day here. And So left off at lesson 12.4, L value references to const, aka non-modifiable. So what we'll do now is we'll do day 26. Is the stream say day 26? It does. Okay, nice. So day 26. And what did we do today? We did intro to compound types, references and pointers. Then we did value categories, L values and R values. Remember, L value evaluates to an object, R value evaluates to a value, i.e. something that changes. L values and R values expressions. Value categories and operators. L value, so remember, L value will implicitly convert to R value, but R value will not implicitly convert to L value. There you go. An L value will implicitly convert to R value will not. How to differentiate. L value references. And the best thing to do for L value references is to use the ampersand directly after the reference type. L value reference types. L value reference variables we did. Modifying non-const L values. Reference initialization, because remember we must do it. A reference will only bind to a matching type. Remember, you can't do int to double. References can't be reseated, so if you did if you do reference of ref to x, but then you do ref equals y, it actually sets ref and x to whatever the y value is. It does not reset or reseat ref to y, because you cannot do that. Yeah. Reference and scope duration, like most variables, they have the set, they die, local variables, they die at the end of the block. Reference and reference lifetimes. So the referent would be x, and the reference would be int ampersand ref. Direct list initialization, and then inside that you would have x. Dangling references, which we'll cover later. References aren't objects because remember they're aliases. And yeah, that was it. Cool. Tutto bene. Today's date is the 26th. Yeah, and that's it. So the next lesson will be L value references. Also got quite a lot to do, but that's okay. So let me leave that there. Cool. So if you did enjoy and are enjoying C++ like me, let me know what you're enjoying. Let me know if you saw something I did that I shouldn't have done in the comments. And yeah, if you can leave a like, subscribe, all that good stuff, comment, and I will see you in the next one where we'll continue with references and pointers.